Right, very good morning. I welcome aboard again to Tone Academy on the T1 channel. What we will do today in today's session is, it will be convenient for you before I actually proceed to the next class, next topic, right, which is important. What I will do is I'll put all the formulae and all the important points that are important for your pre-engineering test or pre-medical test, which you will be writing. It will be convenient for you. One by one, right, I'll be writing all the formulae at one place, right? Let's do it, right? This is number one. So one by one I'm writing it. You can also write down, sit, relax and write down all the important points. This is just enough. What I'm doing today will be just enough for your exam preparation. And if you are lagging in any concept, then I think you can get to the concept, right? What I've discussed earlier. Right, so let us start off with this. The number one, so each formulae or each important point in atomic structure, I will put it as a Roman number, right? And this is just enough for you, right? Observe carefully here, right? The Roman number one, important thing, E is equal to h nu is the formula which predicts dual nature to light. Dual nature to light. So E is equal to h nu. Which of the following is the equation which predicts dual nature to light? If he is asking in the exam, then answer must be E is equal to what? H nu. You must understand this. Right, in which h is a Planck's constant. H is a Planck's constant and whose value will be 6.6 into 10 power minus 27 ergs into second. You must understand. That is the value of what? Planck's constant. You must understand this, right? Now, what is this E is equal to h nu? What type of questions you're supposed to encounter in the exam, right? This E is equal to h nu is nothing but E is energy of one photon. Remember this. This is energy of the one photon. You must understand. Suppose in the exam he is giving you total energy to be 100 ergs, right? And he is asking how many number of photons are there in that given quantity of energy. Then use this equation, because energy of one photon is nothing but h nu. So remember that h is what? The Planck's constant, and nu is the frequency of the radiation which is incident on it. Please understand that. So E is equal to h nu is used for calculating energy of one photon. So in the exam is giving you 20 ergs or 30 ergs or 100 ergs. In 100 ergs quantity, how many are the photons? You can actually use this, because one pencil costs 2 rupees, two pencils cost 4 rupees. That's a simple calculation which you need to do it. E is equal to energy of one photon is h nu. Suppose if the frequency is missing, then we know that nu is equal to c by lambda. So you can actually substitute it, energy of one photon. Mind you, what are we doing here? This equation is to calculate energy of one photon. If frequency is given, use this equation. If wavelength is given, use this equation. Then if I substitute it, it is hc by lambda, and c is 3 into 10 power 8 meters per second, and this is 3 into 10 power 10 centimeters per second. That's nothing but the velocity of light. That value you know very well. And lambda is nothing but the wavelength of the incident radiation. You must understand that, right? So E is equal to h nu is basically what? This is Roman number one. You must understand. Quick revision will help you out in a single page document, right, which I'm trying to explain this here. Just you can actually revise this entire chapter in this fashion, because each Roman number is an important question in the exam. Now, E is equal to h nu is the formula which predicts dual nature for light. You must understand dual nature for light. Second, you know, you can use, what is this E? What is this E? It is nothing but energy, to calculate the energy of one photon. So if you can know the energy of one photon, right, one pencil costs 2 rupees, then 40 rupees, how many pencils you will get it. It's a simple calculation you wanted to do in such way, right? Then use this formula, E is equal to h nu, if frequency is given, and if lambda is given, I think you can use this equation. That is Roman number 1, right? Then I go for Roman number 2, which is important, right? Here is Roman number 2, and please note it down, because this is the revision which will help you out, very quick revision, which will help you out in writing your exam. Here is Roman number 2. Here is Roman number 2. Watch carefully here. Radiation, as we said, when I say radiation, I'm speaking of what? Light, and it has dual nature. Dual nature. When I say dual nature, it behaves as what? A wave in sometimes, and it behaves as a particle sometimes. Now, what do you mean by this sometimes? It's not the question of time. So what we will do here is to explain, right, properties of light. When I say properties of light, I quote few for you. One is the photoelectric effect. Mind you this. The photoelectric effect. Now, if someone is asking you prima facie what is photoelectric effect, then you tell him that it's a property of light. Forget about details. You tell him that it's a property of what? Light. And this property of light can be only explained, can only be explained by treating light as what? Light as particle. You must understand. This is a proof. Photoelectric effect rather is a proof that light is what? A particle. You must understand this, right? This question has been asked n number of times in your exam, right? So which of the following is a proof that light is a particle? Then the answer must be photoelectric effect. You must understand this, right? So it's a direct proof that light is a particle. The best example would be photoelectric effect. Now, what is photoelectric effect? It's nothing but the property of light, right? Similarly, what I'll do, I'll write few more things. Diffraction, you must understand, right? Now, if someone is asking what is diffraction, diffraction is again a property of light. You must understand this. Diffraction, refraction, right? Diffraction, refraction, what is all this? These are all properties of light, and these can be explained only when light treated as what? Treated as a wave. So mind you that there are properties of light, n number of properties of light. Few can be explained by treating light as what? A particle. Few can be explained by treating it as what? Wave. So simply speaking, if you just hang on to any one of this, be it treating as a particle or treating as a wave, you cannot explain all the properties of light. So sometimes, yes, you have to treat it as a particle, as in the case of what? Photoelectric effect, and sometimes it is a wave. So what is the question in the exam? I don't want to go into details because already I have done this. So the question is, which of the following is a proof that light is a wave? Then I think you must be putting a tick mark on what? Diffraction, refraction, or any other properties of light. And coming to the particle effect, where light is a particle, where is the proof? Then I think it must be what? Photoelectric effect. That is the second question which I wanted to take. What is Roman number 2 rather? You know, Roman number 2 is a question where he will ask you light being dual nature. Light exhibiting what? Dual nature, both wave and a particle. That's Roman number 2. I think you have noted it down. Then go for Roman number 3. Observe carefully here, and here comes Roman number 3. Here is Roman number 3. Roman number 3, yes, it's all about the photoelectric effect itself. The photoelectric effect. You get so many questions. On this. You get so many questions on this, the photoelectric effect, right? Now, what is the first question itself? Remember that first of all, I wanted to put in box, it is a direct proof. It's a direct proof that radiation is a particle. Mind you that radiation is a particle. Now, what is the other question which you are supposed to get? If I can put this in box, remember that the equation is h nu is equal to h nu naught plus half mv square. You must understand this. This equation is nothing but the photoelectric equation. This is nothing but the photoelectric equation. Which of the following is a photoelectric equation? If he is asking you, then it is h nu is equal to h nu naught plus half mv square. Now, what is all this? What is all this? Remember that this particular quantity is nothing but the incident energy. Incident energy. And what is this new here? What is this new here is basically nothing but the incident frequency. It's nothing but the incident frequency. You must understand it. It's incident frequency, right? And what about this? This is nothing but h nu naught is the energy which is partly used. It's partly used to kick electron out. Kick electron out, remember. If I'm actually incident energy is 100, 40 or 50 joules of it is used for removing the electron from the clutch of the nucleus. That is what is h nu naught. Sometimes this is also called work function. You must understand this is what is called the work function, right? And this is half mv square, which is nothing but the kinetic energy with which the electron is kicked out. When it's not like a slice that we just remove it and leave it off. We are not doing that. We are providing that much impetus or the energy such that it flies off. Hence, we call it to be an effect. You must understand this, right? So, it's a proof that radiation is a particle. And remember that h nu is equal to h nu naught plus half mv square. And also one critical point which I wanted to mention, in any equation, not only here, in any equation in science, if you have the kinetic energy expression half mv square in any equation, then mind you that it is a mechanical motion and it is a proof that light is a particle. You must understand that, right? That's one case. And if I continue writing on the photoelectric effect, what I will do is I go for Roman number 4 rather. I stick with photoelectric effect, but here is Roman number 4. You must understand. So this is the photoelectric equation. This is the incident energy. It's partly used to remove the electron from the clutch of the nucleus, and then half mv square is nothing but what? The kinetic energy. And here is Roman number 4. Watch carefully here. Roman number 4. Here is the fourth point which I would like to quote. This is the fourth point you must understand. You will get questions on work function. So what is this? H nu is equal to h nu naught plus half mv square. This is half mv square. And this quantity h nu naught is nothing but work function. This is work function, and you will get questions on this work function. Now, what is the thing is, work function depends on what? Work function depends on what? You must understand. Work function depends on what is a question. So, what I'll do, I can write that work function is basically is a function of size of the metal atom rather. Because in photoelectric effect, we use only metals. Metals are placed to the extreme left in the periodic table. In fact, in this case, they are placed to the extreme left bottom of the periodic table, right? So the kicking out of electrons by radiation from the surface of the metal can be called as what? Photoelectric effect. So I think it's not easy to kick the electrons from the non-metal. So I think it's a common sense that you are kicking the electrons from the clutch of the nucleus to the extreme left bottom side. So work function is nothing but the function of the size of the metal atom. It depends on size. If you want the exact relation, then I think work function is inversely related to size. So the smaller the size, the work function or the energy required to remove the electron from the clutch of the nucleus would be extremely difficult for you, right? So understand that the conducive thing is, I think you must understand the photoelectric cells. The photoelectric cells must have big size. You must understand this. Must have big size. So that's why it is potassium, rubidium, and cesium. These are the only atoms used in the photoelectric cells. And mind you, this question has been asked n number of times in the exam. It has been asked n number of times in the exam, so students must remember it's only potassium, rubidium, and cesium. These are the three elements which are very much used in what? The photoelectric effect. Because they have a larger size, bigger size, and the electrons are far away from the nucleus, they are diffusing and relaxing. In that case, it becomes easy for us to remove the electron from the clutch of the nucleus. That energy which you utilize is nothing but the work function. So the work function and the size are basically inversely related. You must understand this. This is one question which he will be asking in the exam, right? That is the fourth one. Now coming to the fifth one, well, I would like to highlight something which is extremely important for you. Extremely important. And I think this one, the fifth one, you can actually bank on it. Bank on it in the sense you will get it 100% in the exam, whatever you will be writing, right? So what is the fifth one? So I call this to be extremely important, very important. You must understand this. This two things which I would like to write with respect to photoelectric effect, right? So what's the question? The following statements, right, are true with respect to the photoelectric effect. The photoelectric effect. You must understand that I'm writing the two statements which are extremely important, and you can bank on this because these will be given in the exam. You must understand this. The very first one which I would like to say, that intensity. Now what is intensity? Mind you that intensity is the number of photons that are striking a unit area. Right? When I say intensity of radiation, well, intensity of radiation, right? Intensity of radiation. Remember, if you actually recollect what is there in the photoelectric effect, you mind you that if one photon is striking one electron, only one electron is kicked out, right? And if two photons are striking the surface of the metal, then two photons are kicked out. So what you're doing is, if the intensity is increasing, then what is happening? Intensity of radiation increases. Then only number of electrons just increase. That's all. The number of electrons that are kicked out increase. So when intensity increases, it is the number of electrons that are kicked out increases. Nothing more than that, right? And I would like to highlight. So not the kinetic energy. You must understand. Simply speaking, it implies that kinetic energy of ejected electron does not depend on intensity. You must understand. So intensity is basically independent of the kinetic energy of the electron. You must understand this. Because when you increase the intensity, only one photon will strike out one electron. Two photons strike out two electrons. Three photons strike three electrons. Or 100 photons will strike only 100 electrons. But what is common in all this is basically all these electrons that are ejected will be having the same kinetic energy. You must be understanding it, right? So when intensity increases, it is just the number which is increasing, but what is common in all this is the kinetic energy remains what? Same. So that is the first statement which I would like to say. Right, the intensity of radiation increases, then only number of electrons that are ejected increases, and it has nothing to do with the kinetic energy. That's why I say the kinetic energy of the ejected electron does not depend on what? Intensity. That is the first question. And the second one, which I would like to write it for you, is this. What is the second statement which you can bank on, which you will get it in the exam? Is this one. Right, to alter kinetic energy, or to change the kinetic energy of ejected electron, to alter or change the kinetic energy of the ejected electron, you must be changing, you please alter incident frequency and not intensity. If you think that increasing intensity will change the kinetic energy of the electron that is ejected, you are mistaken. To change the kinetic energy of the electron, you must be focusing on the incident frequency or the incident wavelength of the radiation which is striking it. If you keep constant the incident frequency, then I think the number of electrons ejected, it can be in infinite in number, but all these infinite number of electrons will be having the same kinetic energy. You must understand. So simply speaking, what I mean, I can simply say intensity independent of kinetic energy, or kinetic energy is independent of what? Intensity, whatever. But I think kinetic energy varies only with frequency. You must understand. These two are the two things which I wanted to convey. Hope I have conveyed it and you remember till you write your exam. That's Roman number 5. Go for Roman number 6. It is important. Let us see. What is Roman number 6? Let's see what is Roman number 6. You get the questions on spectral lines and spectra. So what I will do, right, regarding spectra, if it is 6, then I think you can see regarding spectra. Here are the questions. First of all, understand atoms give. Right? The atoms basically give. Remember, they give discontinuous spectra. Or otherwise, we have the other name for it. Rather, atoms give line spectra. You must understand, they give discontinuous spectra and line spectra. You must understand this. Now, what is line spectra? You know, when there is electrons jumping within the shells, the light that comes out goes through the slit of a spectrophotometer, and the slit image is formed as a line. You must understand. So line spectra somewhat looks like this, and remember that each line has great gaps. You can actually distinguish the gaps like this. You can actually see these, and these are basically well-defined lines. Now, when I say well-defined lines, each line's lambda, wavelength, frequency, or any other parameter with respect to the radiation which is giving you this line spectra is clear, distinct and clear. That's what I call it to be a well-defined line, right? So this is one case. And remember that molecules give band spectra, which I'm not discussing here. After all, we are discussing atomic structure. So what does atoms give? Atoms give discontinuous spectra, that is the truth, right? And you can see discontinuous means each line is not merging with the other. If each line merges with the other, it looks like a band of lines. So we call that to be what? Band spectra, which is given by molecules, not atoms. I'm not discussing molecules here. So remember that atoms give what? Discontinuous spectra, atoms give line spectra, and these lines are something like this, which you will be in a position to define all the parameters of these lines like wavelength, frequency, and you have a clear distinction or clarity with respect to these lines. Hence, we call that to be a well-defined lines. Now, what are the other things which are important, right, with respect to the spectra? I stay on to the 6th itself, and here is some more things which you must be understand this, right? And here is, you can say, you can actually change it to 7 rather. 7 rather, and here it is a question. Remember this, right? Now what is this? Remember, to calculate number of spectral lines when electron jumps from an nth energy level. Now it has gone to the nth energy level by actually accepting or absorbing some energy, and it's trying to come down. Now he's asking how many number of spectral lines can be done here. Then I think you can understand and write down this formula. It is n into n minus 1 by 2. Right? Suppose if it is gone to the 10th energy level and it's coming down, then it is from the 10th energy level to which energy level, it doesn't matter. It can jump to 9, it can jump to 10, or it can be jumping to 8 or 1 or second. But I think how to calculate, each jump will give you a line in the spectrum. Right? So how many lines can be produced? If he is asking that, then it is basically 10 into 10 minus 1 by 2. That is 10 into, this is 9, which is right 90 by 2. This is 90 by 2, which is 45 lines, right? So whatever energy level it might go, right? So how many lines can be produced? If he is asking, then I think use this formula n into n minus 1 by 2, where n is the nth energy level to which it is getting excited. Now other than that, I would like to quote something here, and watch here. Suppose if he says it is jumping from one energy level to another energy level. Right, he is specifying the quantum numbers. Suppose if he is specifying the quantum numbers, it is jumping from the 5th energy level to the 1st energy level. So he is mentioning that. To which energy level it is jumping. Here it's nothing like that. He did not fix it. It has gone to the 10th energy level and you're supposed to come back, then how many times and what installments it will be doing it. That's the first question. Suppose if it's specifying that it is jumping to the first level, then use this formula, that is sigma delta n. For example, suppose if an electron is jumping from 5th to 1st, right? 5th to 1st, then delta n is nothing but 5 minus 1, which is nothing but 4, right? Because it's delta n is nothing but the difference of the energy levels, which is jumping 5 to 1 is 4. And then you need to put sigma, which is sigma 4. Sigma is nothing but 4 plus 3 plus 2 plus 1 plus 0. So this is 7, 9 and 10 lines. You need to put it in the exam. You must understand. So simply speaking, if only one quantum number is issued to you, use this. If two quantum numbers are issued to us, then you subtract it and make a sigma. Sigma is the sum. So I think you can get sigma delta, and that is total equal to what? 10. That's regarding the spectra. So few things, atom gives what? Discontinuous spectra, and then use this formula for calculating the total number of lines. Right, then we move on. This is Roman number 7, and I continue to write all important formulae. Watch carefully here, and here comes the next formula. Please note it down, right? Please note it down and just go in for this particular document, what I'm writing, put it as a complete document and just go through it till you write your exam. You must understand. And here is the next point, which is 8, which I would like to call, and watch it here, right? For a circular motion, that when I say circular motion, I'm referring to the Bohr's theory now. For a circular motion, mind you that total energy is equal to Ke plus P, right? The total energy is nothing but the kinetic energy and the potential energy of the electron that is revolving in the circular orbit. Now, what are the questions in this? There are one question which is for sure. This is for sure, right? You can bank on it. This is for sure. Mind you that total energy by kinetic energy is minus 1. And please note it down. What he will do is in the exam, he will give you kinetic energy, right? So he will give you kinetic energy, he will ask you total energy. If the kinetic energy is 20 joules, which is giving you, if he is asking you kinetic energy, it will be minus 20. So the relationship between total energy and kinetic energy is -1, you must understand. Suppose, if he is asking potential energy and kinetic energy relation, then it is P is minus 2K. P, potential energy, is minus 2K. Potential energy is always minus because you are spending, you are actually spending work or energy to do work, so it will be always minus, and potential energy is minus K, or I can simply say potential energy by kinetic energy. Potential energy by kinetic energy is -2. You must understand this. So those are the relations which you will get in exam, and mind you that this has been asked n number of times. Mind you, total energy by kinetic energy is -1, so the difference is only -1. That is the first question, you will get it, right? Continuing with this, and here comes the ninth one. Observe, here is the ninth one. You must understand, all these are important. Here is the ninth one. Well, to calculate energy of nth orbit, to calculate the energy of the nth orbit, we have many formulae. The first one is En, a minus 13.6 by n square electron volt. Right? That is in electron volts. Now, what is electron volt? If you remember, the force experienced by an electron in moving through a potential difference of 1 volt. So, to move an electron from one point to the other, you require potential difference. If the difference is 1 volt, then the work done by you, or the kinetic energy of the electron, or the force experienced, all are synonymous statements. That can be called as what? Electron volt. It's a unit of what? Energy, which we'll be frequently using it. And no sir, we don't want it that, then I think you can use this 2.179 into 10 power minus 11 ergs by n square. Right? This is another equation. And suppose if you wanted to do this in joules, energy is minus 2.179 into 10 power minus 18 by n square, and that is joules, you must understand. So you can calculate energy of the first orbit, second orbit, third orbit, and mind you that you have infinite orbits, and you can use any of these equations to calculate what? The energy of the nth orbit given, right? So remember, use any of this, and that is how it is. And then I go for the 10th one. Now, what is the 10th one here? Now, here is another question. Mind you that 10th, he will ask you velocity of electron in the nth orbit. In the nth orbit, mind you, velocity of the electron in the nth orbit, that's energies in the nth orbit, this velocity of electron in the nth orbit. And then you can use this formulae, Vn is equal to V1 by n, and V1 is 2.18 into 10 power 8, 2.18 into 10 power 8 centimeters per second. So I can simply say V2 is V1 by 2 and V3 is V2 by 2. So similarly you must understand. So what is the inference from what we are getting from this is, as you move away from the nucleus, the velocity is actually falling, the kinetic energy decreases, and the potential energy would be what? Increasing. That's what is the expression showing it to you, and it is the velocity of the electron, and the velocity of the electron is 2.18 into 10 power 8 centimeters per second. That is the velocity of the electron in the first orbit. You must understand. So he has calculated the energy of the nth orbit. He has calculated the velocity of an electron in the nth orbit. Strange. It is very strange and surprising because we don't see an atom, but I think things have been calculated and put forward to you. That's a great thing. That's a legendary thing. You must understand. That is the 10th one. And here I go for the another expression for you. Another expression for you, and watch carefully here. And the 11th is basically radius of orbit. Radius of nth orbit of Bohr. Radius of nth orbit of Bohr. Then if he is asking you, then you must understand this, that Rn is equal to 0.529 into 0.529 angstrom units. You must understand. Right, into n square. It is nth orbit, so into n square angstrom units, you must understand. Otherwise also you can say Rn is equal to 0.529 into n square into 10 power 1 angstrom unit is 10 power minus 8 centimeters, you must understand. So if I can find the radius of the first orbit, it comes to 0.529 angstroms, or otherwise equal to 0.529 into 10 power minus 8 centimeters. You must understand this. So that is the radius of the nth orbit, you must understand. Now if I can extrapolate this, then so there is the radius equation. You can go in for finding radius of R1, R2, R3, R4 till the nth orbit. That's how you have to use it. Now suppose if I extrapolate this, then remember one point here. I am writing these two equations for you very quickly. This is the 12th one. Then I think energy equation En, right, is minus 13.6 by n square electron volts. Our radius of the nth orbit is 0.529 into n square angstroms. These two equations which he has proposed by Bohr are only for hydrogen atom. Is only for hydrogen atom. You must understand, right? It's a single electron system. Right, for all other atoms, if you wanted to extrapolate it for all other atoms with an atomic number Z, right, what you do for other atoms, right, you can apply this formula with atomic number Z. Suppose if Z is the atomic number, this is only for hydrogen atom which Bohr was proposing it. If you wanted to apply for other atoms, right, with atomic number Z, but those are also single electron systems only, mind you that, but their atomic number remains to be Z, then I think you can use this radius of nth equation, and mind you that this is En is equal to minus 13.6 by n square into what? Z square electron volts. You have to multiply that with what? Atomic number square electron volts. And suppose if you want to apply that for the radius equation, Rn is equal to 0.529 into n square by Z. So for all other single atom, see, first of all, Bohr series is only applicable for single electron systems. Single electron system means all those species, radicals or atoms which have one electron. Suppose if you wanted to apply it for single electron systems with varying atomic number, but remember they remain to be single electron systems only with varying atomic number, then I think you can use the same formula but multiply with what? Z square, and divided by what? Z. So you must understand this. You have to use this formula for in case you are applying or extrapolating this for other atoms, other single electron systems, radicals, ions, right, with atomic number Z. You must understand. So that is 12. You must understand this. Then coming to the other equations, watch carefully here. The other equations is this 13, right, and here comes one of the drawbacks which I can actually tell you of Bohr, right. So please understand that this is 13. One of the biggest drawbacks of Bohr, he cannot explain, cannot explain, right, this guy, even though he's great in his approach by proposing the non-radiating path of the shell, everyone have their, errors, everyone have their, drawbacks. Similarly, Bohr has drawbacks, and this fellow cannot explain two things. One is the Stark effect, and the other is the Zeeman effect. You must understand. Now, what is the Stark effect and what is Zeeman effect? You must understand here. Now, as I told you, I was actually telling when I was delivering the concept, if you ask Bohr n number of times, infinite number of times also, where is the electron? In his life, he has only one word, that is nothing but shell or non-radiating path or the orbit or the stationary orbit. Other than that, he doesn't know anything. right? That is the only thing which he will be telling you, even though you question him a number of times. Now, if that is the case, people get suspicious, and what they do is, they have taken their spectra, and this is the line which is given by the Bohr's application when we actually go in for hydrogen spectra. And suppose if an electron is jumping from a fourth orbit to the first orbit, the line is, you got this line. And what they have done, they have applied magnetic field here. Magnetic, and here is another magnet. And when you apply magnetic field, right, to that spectra line, this line is actually further splitting into several lines. It is basically further splitting into several lines, indicative of the shell being split into further divisions as subshell. And if you dial Bohr and ask him, man, when I'm applying a magnetic field to it, your line, your so-called shell where you received your Nobel Prize, it is further splitting into further things, then what can you say about the explanation? He says, I don't know about it. I only know about what? Shell. When you claim that you do not know the explanation for that, then I put it to be a drawback. Right? So some fellows, what they have done, they have removed the magnetic field and they applied electric field. So that's called a Stark effect. The splitting of a spectral line in an electric field is called Stark. You can actually see the rhyming word, electric and Stark, right? Both are rhyming. Then the line is further splitting, which Bohr cannot explain, right? If you put magnetic field, it cannot explain the splits in the lines. So both can be considered to be drawbacks of Bohr, and the splitting of lines in presence of magnetic fields and splitting of lines in presence of electric fields. This can be called as magnetic fields and magnetic Zeeman effect and Stark effects respectively, which will be asked in your exam. You must understand, right? One of the biggest drawback of Bohr is this, which I would like to quote. And then coming to the other ones, that is, if I continue writing the 14th point, which is extremely important. The 14th point. Right? And what is the 14th point? It is nothing but the Heisenberg's uncertainty principle. It is Heisenberg's uncertainty principle. You must understand. And what is Heisenberg's uncertainty principle's equation? It is basically delta x into delta p is greater than or equal to h by 4 pi. You must understand this. This is the Heisenberg's uncertainty principle. Otherwise, actually, we can write this as delta x into m delta v is greater than or equal to h by 4 pi. You must understand, right? This is the thing. What is this? The product of errors is constant, where delta x is error in position. Now, position has a value centimeters. It's nothing but the distance of the nucleus to a particular orbit. That's nothing but the radius which is found out by Bohr. Right? I explained this. If you wanted to know the concept delivery, please revise back and go to that. You will have a fantastic word, the concept delivery, which was delivered by me. Right? And then delta V is nothing but the error in velocity. You must understand. Error in determining what? Velocity, which is completely ignored by Bohr, where these errors were exceeding the actual values, and thereby it created a problem for Bohr. You must understand this. So Heisenberg's uncertainty principle, basically this Heisenberg's uncertainty principle, this basically contradicts the Bohr's model. So Bohr's model is basically confident about giving the address of the electron. The electron is there in the particular shell. But this fellow says it's impossible to determine both radius as well as velocity at the same time for a dynamic particle or a subatomic particle like electron. I think this, I have done it very clearly. You can actually revise it back. So this is the basic thing. And the other things with respect to Heisenberg's uncertainty principle is two things which I would like to write. Number one, right? HCH uncertainty principle. This is basically applicable. This is basically applicable only to subatomic particles. That's all. There is a limitation for what? Heisenberg's uncertainty principle. It's not for macro objects. It's only for what? Subatomic particles like electron. That's all. That is the only limitation. So his target is basically Bohr, who is boasting of his energy equations, radius equations, velocity equations, and he has targeted him by telling that it is just impossible to determine what together at the same time. So what is delta x is the error in position. What is delta p is the error in momentum. But otherwise you can write this momentum to be mass into velocity. Mass doesn't change. So it is basically what? Delta v. You must understand this, right? That is the 14th point which I would like to say. Then coming to the 15th point, here comes the other one. Here comes the other one. Right? What is the other one? You must understand. Then that is, 17th point, if I can write it for you, you have a de Broglie's equation. The de Broglie's equation, where I think to calculate, lambda is h by mv. Right? You must understand first, visualize electron to be a wave. And that means that electron is a wave. That is a reality. And if you wanted to find out the distance between the crest and the trough, and if this is lambda, and the lambda can be found out using this formula, where m is the mass of electron, which is 9.1 into 10 power minus 28 grams, you must understand this, right? And v is nothing but the velocity of the electron, and h is a Planck's constant. You must understand this. So use this lambda is equal to h by mv to determine the wavelength of an electron. It looks strange. It looks strange because wavelength is only told for waves. So you can question me, is electron a wave? And of course, yes, it is a wave. And the wavelength is given by h by mv. You must understand this, right? And that is one. And if you wanted to extrapolate this for something else, then I think you must understand this, that lambda is equal to, there are two things you must understand. You can mix it off. You can mix this, mix it up. You can actually basically mix it up, two things. One is k is equal to half mv square, right? And lambda is equal to h by mv. If you mix it off, then lambda is equal to square root of, if you mix it off, they substitute, lambda is equal to h by mv, then you will actually get a relationship between lambda and k. Lambda and k also, because k is half mv square, and then lambda is equal to h by mv, then substitute the value of v here, then you always get a relationship between lambda and k, and that will be a question in what? Exam. That I think you must be solving it, right? So lambda is h by mv, k is half mv square, mix it up, and then you will have a relationship between lambda and what? Kinetic energy. You must understand that might be also a question in exam, right? That is de Broglie's equation. Then coming to the 18th point, watch carefully here, watch here, right? Watch here. And the 18th is the wave mechanical model. Wave mechanical model, that's nothing but the Schrodinger's wave equation. The Schrodinger's wave equation, you must understand. And in the Schrodinger's wave equation, right, what is Schrodinger's wave equation? If you actually recollect it, Schrodinger's wave equation, then I think you can actually see dou square psi by dou x square plus dou square psi by dou y square, dou square psi by dou z square plus 8 pi square m by h square into E minus V into psi equal to 0. That's basically the Schrodinger's wave equation, and this is nothing but a differential equation of second order. Differential equation of what? Second order. Now, what is the question in the exam is, if you solve for psi, every equation has a solution, right? If x plus y is 5, then you are finding the solutions of x and y. Similarly, in Schrodinger's wave equation, you are actually solving it for psi, and the psi values, the psi solutions are very strange. In fact, psi solutions are nothing but quantum numbers. Quantum numbers, and the quantum numbers are n, l, m, and not what? S. That might be a question in exam. Which of the following is not a solution of Schrodinger's wave equation? The answer is what? S. because N, L, M have something in common. They represent spaces, whereas S represents only a spin. So that's like an odd man out. So which of the following is not a solution of the Schrodinger's wave equation? If someone is asking, it must be spin quantum number, not the other three, because all the three others represent what? Spaces, right? That is the 16th one. That is the 18th one. Then you have the other point, that is, 19th. What is the 19th point, which is extremely important for the exam? Right, here comes the 19th one. 19th one. Well, you know the deviations from the Aufbau's principle, which is very, very important. Now remember deviations, or I cannot say deviations, I can say violations of what? Aufbau principle. Violations of Aufbau principle you will actually see while writing the electronic configurations. Well, writing the electronic configurations of what? Copper and chromium. Copper and what? Chromium. And chromium, actually, if you see the actual configuration, right? Actual configuration according to Aufbau, rather. Now, I don't call it to be actual, but I think chromium, its configuration, if I can write it short, the outermost configuration, so it should be 4s2 3d4, but in real it is actually 4s1 3d5. This is correct, this is wrong. Similarly, you can say 4s2 3d9, and actually if you see it is 4s2 3d10. This is wrong, this is right. And I gave you a clear explanation while explaining the Aufbau principle that the difference between the shells is 2 less, right? If the difference between the subshells is 2 less, right, the electronic configurations get violated. So as you are actually moving out from the nucleus, far away from the nucleus, the energy difference between the shells decrease, and naturally the energy difference between the subshells also what? Decrease. So you have violations here. And in F block you can actually see in F block you will have further violations in what? Aufbau's principle. You must understand, you have further violations when you are actually going off from the nucleus. Because I say F block, because it belongs to what? 6th energy level, right, where you have the F block lanthanides, where you always have violations. So Aufbau principle, the scheme of distribution of electrons within the shell, is violated when you move away from what? The nucleus, right? That is the 19th one. Here comes the 20th one. You must understand here, this is extremely important, and this is 20th one. This is to calculate lambda of electrons, of radiation or of light emitted during each and every transition in hydrogen spectra or any single electron systems. To calculate lambda or the light emitted when electron jumps from a particular energy level to a lower energy level in hydrogen spectra, then I think use what? The Rydberg's equation. The Rydberg's equation, you must understand the Rydberg's equation. Now what is this? It is basically 1 by lambda is equal to R into 1 by N1 square minus N2 square. You must understand that is how we calculate the lambda which is emitted during each and every transition in hydrogen spectra. Right, that is one thing, where R is called the Rydberg's constant. Rydberg's constant, whose value is 109677 inverse centimeters approximately. This is inverse centimeters. Inverse centimeters, you must understand. That is Rydberg's constant, where N1 is the lower energy level, N2 is the higher energy level, where the electron is jumping from higher orbit to a lower orbit. You must understand the Rydberg's equation is basically used to calculate the light emitted, the lambda of the light emitted during each and every transition in the hydrogen spectra, right? That is one. And then coming to the other one, that is 21st point, right? 21st point, here is the case right, it is calculating smallest lambdas in each series in hydrogen spectra, to calculate the smallest lambdas in each and every series in the hydrogen spectra. Now when I say smallest lambda, that's nothing but, well, I would like to say smallest lambda is nothing but the limiting point, or I can simply say the limiting lambda. I call this to be limiting lambda, right? And you have several series. One is Lyman, right? And in Lyman, well, N2 is equal to infinity and N1 is equal to 1. So what is a limiting lambda is nothing but a jump from infinity to a particular energy level. So from infinity to a particular energy level, that is 1, we call this to be Lyman series limit. So what you do is, how much is the Lyman series limit? Then I think R into 1 by 1 square minus 1 by infinity square, which we need to substitute in the Rydberg's equation. So the smallest lambda is got by substituting N1 is equal to 1 and N2 is equal to infinity in a Rydberg's equation. Then you get this. Then I think 1 by lambda is equal to R into 1 by 1 minus 0. Or I can simply say lambda is 1 by R. This lambda is called Lyman series limit. Lyman series limit. So what is a series limit? Series limit is not a bigger lambda. It is the smallest lambda of that particular series, right? In the exam, I have seen people asking you questions. Lyman series limit is, in the options he'll give you 1 by R, 2 by R, 3 by R, 4 by R. The answer is 1 by R. Similarly for Balmer, what you do is Balmer series limit. If you wanted to calculate the smallest lambda in Balmer, then I think N2 will be infinity. N2 will be infinity, N1 will be 2, right? Similarly, bracket, similarly passion, similarly fund. The only thing which you need to change is N1 is equal to 1, 2, 3, 4 and 5. N2 remains same. Then you are supposed to get the smallest what? A lambda. If I can calculate Balmer for you, then I think for Balmer series limit, watch carefully. For Balmer series limit, right? Then substitute N2 is equal to 2 and then N2 will be infinity and N1 is equal to 2. Then I think 1 by lambda is R into 1 by 2 square minus 1 by infinity square. So if you can calculate, then 1 by lambda is equal to R by 4. Or I can simply say lambda is equal to R by 4. So it is, lambda is equal to, right? Lambda is equal to, right, that's 1 by R, this is 4 by R, you must understand this. Right, so Balmer series limit is, in the exam he'll ask you 1 by R, 2 by R, 3 by R, 4 by R. The answer is 4 by R. If it is Lyman, it is basically 1 by R, 2 by R, 3 by R. It should be what? 1 by R. You must understand this, right? These are the formulas which you should be revising it, because it can be 1 or 2 questions which are asked in the entire atomic structure. Remaining all are theories, Aufbau principle and Pauli's exclusion principle, etc. that I have already explained. So all the formulae at one place. You must be practicing this and be confident in writing the exam, because what happens is you cannot go blindly and write down ABCDs in the exam, but rather you must be checking out at least, you must apply your mind, because you have gone through some concepts, because blind guessing always goes wrong, right? And we will discuss one more chapter in the next class, right? Sit, relax, have a 100-page document of all the important questions in any chapter. Then I think you will be confident and you will be writing the exam in much better way, right? So if you have any issues with the content delivery, then I think go back and revise it. But otherwise, while revising, please remark it in your paper and have a 100-page document in any topic which you are revising. Thank you.